Suppose an electronic control unit calculates the correct answer. The sensor value is valid, the algorithm is correct, and the output command is exactly what the vehicle needs. But the command arrives after the required moment. Is the system correct? In a real-time system, the answer can be no. Functional correctness depends not only on what result is produced, but also on when that result becomes available. Real-time does not simply mean extremely fast. A function taking 20 milliseconds may be acceptable when its deadline is 50 milliseconds. Another function taking only 2 milliseconds may still fail if its deadline is 1 millisecond. The important question is whether the complete response finishes within a defined time constraint. A deadline is the latest permitted time for a required result or action. It is normally measured relative to an event, such as a timer release, sensor transition, received message, or detected fault. Consider an automatic windscreen wiper controller. A rain sensor indicates the amount of water on the windscreen. The software reads and validates the measurement, determines the required wiping mode, and produces a logical command. Lower software then updates the output hardware, and an external motor driver controls the wiper motor. The relevant timing chain does not begin only when the control algorithm starts. It may begin when the measurement becomes available or when a periodic timer releases the processing. It ends only when the defined useful response has occurred, such as the new command being accepted by the output path. This is called an end-to-end timing requirement because it covers the complete chain rather than one isolated software function. The wiper controller may execute periodically. For example, a conceptual control cycle might be released every 20 milliseconds. Periodic means that execution is requested at a repeating interval. Other activities are event-driven. Pressing the washer switch, receiving a vehicle mode message, or detecting an output driver fault may create an event that requires a response. Some events are sporadic. They do not occur at a fixed period, but the system assumes a minimum separation between successive occurrences. Several timing terms must be kept separate. Execution time is the time during which a software function actually uses the processor. Response time is the total delay from the function becoming eligible to execute until its required processing is complete. Response time can include waiting for higher priority work, resource blocking, interrupt activity, and the function's own execution. End-to-end latency can include even more: sensor acquisition, software processing, network communication, driver updates, and hardware response. Jitter is variation in timing. If a periodic activity is intended to start every 20 milliseconds, but sometimes starts slightly early or late, that release variation is jitter. Output jitter describes variation in when the result becomes available. Small timing variation may be acceptable for one function and unacceptable for another. The permitted amount must come from the requirement, not from a general rule. Slack is the remaining time between completion and the deadline. If a response finishes in 8 milliseconds and the deadline is 15 milliseconds, 7 milliseconds of slack remain. Slack is useful, but it should not be treated as spare processing time that can be consumed without analysis. Real-time requirements are often described as hard, firm, or soft. For a hard real-time requirement, missing the specified deadline is considered unacceptable. The system must be designed and verified so that the deadline is met under the defined operating conditions. For a firm real-time requirement, a result arriving after the deadline may have no useful value and may be discarded, even though an occasional miss may not immediately constitute total system failure. For a soft real-time requirement, latency reduces quality but can sometimes be tolerated. A delayed infotainment animation is different from a delayed safety-related control response. These examples illustrate the categories, but an engineer must never classify an automotive function using intuition alone. The classification, tolerated failure behavior, and required reaction must come from system requirements and, where applicable, safety analysis. Average execution time is not enough to prove real-time performance. Imagine that the wiper calculation normally finishes in 1 millisecond, but sometimes occasionally takes 6 milliseconds because it follows a longer software path, waits for shared memory, or is interrupted by more urgent processing. The average may appear excellent while the rare worst case violates the deadline. Worst case execution time, or WCET, is an upper bound on the processor time required by a software unit under defined assumptions. Worst case response time is broader because it also accounts for factors such as interference and blocking. Possible sources of delay include higher priority tasks, long interrupt handlers, locked shared resources, memory contention, communication delays, variable software paths, and excessive system load. A deadline miss can also create a chain reaction. If a periodic task is not finished before its next activation, the new work may arrive while the previous work is still active. This is called an overrun. Depending on the design, executions may queue, be skipped, replace older data, or trigger fault handling.
There is no universally correct overrun response. Continuing with old sensor data, dropping an activation, or resetting an ECU can each be wrong in a different system. The required behavior must be designed explicitly. Using a real-time operating system does not automatically make an ECU real-time. The operating system can provide mechanisms for controlled task execution, priorities, events, and timing-related supervision, but the complete software still requires correct configuration, bounded execution, suitable priorities, and validated timing budgets. In AUTOSAR Classic, application behavior is implemented through runnables that are integrated into operating system execution contexts. The RTE and generated integration connect application events with the configured execution environment. The precise mapping depends on the ECU configuration. Real-time verification combines analysis and measurement. Engineers identify timing requirements, estimate or determine execution bounds, analyze interference and blocking, measure execution on representative target hardware, and test overloaded or abnormal conditions. The longest duration observed during one test is not automatically the true worst case. Testing can reveal timing problems, but evidence of bounded behavior also depends on architecture, assumptions, analysis, and coverage of relevant execution paths. If an interviewer asks what makes a system real-time, do not say only that it uses a fast processor or an RTOS. Explain that correctness depends on meeting defined deadlines and that engineers must consider worst-case execution, response time, latency, jitter, interference, blocking, and overload behavior. Return to the automatic wiper. The timer releases the cycle. The sensor value is acquired and validated. The application selects the wiping mode. Lower software updates the command, and the motor driver receives it before the deadline. Every stage consumes part of the timing budget. That complete bounded chain is the real-time system, not merely the calculation in the middle. Subscribe to continue turning these embedded fundamentals into practical interview-ready AUTOSAR knowledge. The next lesson opens the execution timeline and explains how interrupts, tasks, and scheduling decide which software runs, when it runs, and what can delay it.